When we talk about exploring space, we usually focus on destinations: the Moon, Mars, the moons of Jupiter. Exciting places with interesting geology and the possibility of finding life. But there's a question that gets overlooked in all that excitement. How long does it actually take to get anywhere? It is more sobering than most people realize, because space isn't just big, it's empty. And that emptiness creates travel times that challenge everything we think we know about exploration. In this video, we'll calculate how long it would take to reach two destinations: Pluto, the most famous dwarf planet at the edge of our solar system, and Proxima Centauri, the closest star to our sun. The answers are not encouraging. Pluto is often described as being at the edge of the solar system. That's not quite accurate. The solar system extends much farther, but Pluto is certainly remote by any human standard. It orbits at an average distance of 3.7 billion miles from the Sun. That number is hard to feel, so here's a comparison that might help. Light is the fastest thing in the universe. Nothing travels faster. When you flip a light switch, the light appears to fill the room instantly. But light isn't actually instant. It just moves so fast that we can't perceive the delay. Light travels at 186,000 miles per second. At that speed, it covers the distance from the Sun to Earth in about 8 minutes. The same light takes 5.5 hours to reach Pluto. Think about what that means. If the Sun suddenly went dark, we on Earth would know about it 8 minutes later. Pluto wouldn't find out for another 5 hours and 22 minutes. By the time the darkness reached Pluto, we'd have already had time to panic, call our families, and start wondering what comes next. At Pluto's distance, the Sun doesn't look like the blazing disk we see from Earth. It's just a very bright star, about 1,000 times brighter than a full moon, but concentrated into a single point of light. Enough to cast shadows, but not enough to warm anything. In January 2006, NASA launched a spacecraft called New Horizons. Its mission: become the first probe to visit Pluto and send back detailed images of this distant world. New Horizons holds a record. It's the fastest spacecraft ever launched from Earth. Not the fastest spacecraft overall. That honor belongs to the Parker Solar Probe, which uses the Sun's gravity to accelerate, but the fastest at the moment of leaving Earth. Within 9 hours of launch, New Horizons had already passed the Moon's orbit. For comparison, Apollo astronauts took 3 days to cover that same distance. New Horizons was traveling at approximately 36,000 miles per hour. At that speed, you could fly from New York to Los Angeles in about 4 minutes. You could circle the entire Earth in just over 40 minutes. So how long did this record-breaking spacecraft take to reach Pluto? 9 years. New Horizons launched on January 19, 2006, and arrived at Pluto on July 14, 2015. Despite being the fastest thing humans have ever sent into deep space, it still needed nearly a decade to cross the solar system. Here's something most people don't realize about the New Horizons mission. The spacecraft never stopped at Pluto. It couldn't. To slow down and enter orbit around Pluto, New Horizons would have needed to carry enormous amounts of fuel. Fuel is heavy. A heavier spacecraft needs more fuel to accelerate, which makes it heavier still, which requires even more fuel. It's a vicious cycle that rocket scientists call the tyranny of the rocket equation. So, instead of stopping, New Horizons performed a flyby. The spacecraft screamed past Pluto at tremendous speed, capturing as much data as possible during an encounter lasting just a few hours. It photographed the surface, it measured temperatures, it analyzed the thin atmosphere, and then it continued on into the outer solar system, never to return. Today, New Horizons is still traveling outward, now more than 5 billion miles from Earth. We got our pictures, but we only got a snapshot, a brief glimpse during a single pass. Despite the brief encounter, New Horizons revolutionized our understanding of Pluto. Scientists had expected a dead world, frozen, cratered, geologically inert, unchanged for billions of years. What they found was far more interesting. Pluto has mountains, tall ones, reaching 11,000 feet, comparable to the Rocky Mountains. These peaks are made of water ice, which at Pluto's extreme temperatures of minus 390 degrees Fahrenheit behaves like solid rock. There's a heart-shaped glacier larger than Texas, made of frozen nitrogen. Part of that glacier, a region called Sputnik Planitia, has no visible impact craters. None at all. That's significant. In the solar system, surfaces accumulate craters over time as asteroids and comets strike them. A surface with no craters is a young surface, geologically speaking, or one that's being actively renewed. Something on Pluto is erasing the craters. Something is resurfacing the terrain. Billions of miles from the sun, this frozen world appears to be geologically active. Even more intriguing, the evidence suggests Pluto may have a liquid ocean hidden beneath its frozen exterior. Water, kept liquid by internal heat from radioactive decay, possibly existing right now beneath miles of ice. Life? Probably not, but liquid water where none was expected changes how we think about where oceans can exist. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. New Horizons gave us a taste, but to really understand Pluto, to confirm the ocean, study the geology over time, watch the seasons change, we need to go back and stay. NASA has proposed a concept mission called Persephone that would orbit Pluto for years, studying it in detail the way Cassini studied Saturn for over a decade. The problem? Getting there. A spacecraft designed to slow down and enter orbit needs to carry fuel for deceleration. More fuel means more mass. More mass means slower travel. The proposed timeline for Persephone launch in 2031, arrive at Pluto 2058. That's 27 years of travel time, nearly 3 decades. Think about what that means for the people involved. A researcher who helps design the mission in their 30s would be approaching retirement when it arrives. Graduate students who analyze the first orbital data might not have been born when the spacecraft launched. Entire careers would pass during the cruise phase alone. Pluto is at the edge of our solar system, and even that edge takes a generation to reach properly. Everything we've discussed so far, Pluto, the 9-year flyby, the 27-year orbital mission, all of that is still within our solar system. We haven't even approached the edge of interstellar space. The stars are something else entirely. The closest star to our Sun is Proxima Centauri. It's a small red dwarf, part of the Alpha Centauri triple star system, sitting 4.25 light-years away. That's approximately 25 trillion miles. Here's a way to feel that distance. Pluto is about 3.7 billion miles from the Sun. Proxima Centauri is roughly 6,800 times farther than Pluto. If Pluto is at the edge of your backyard, Proxima Centauri is in another city, a distant city, one you need to take a plane to reach. Proxima Centauri isn't just the closest star. In 2016, astronomers confirmed something remarkable. It has at least one planet orbiting in its habitable zone. This planet, called Proxima b, sits at a distance from its star where liquid water could theoretically exist on the surface. It receives about the same amount of energy from Proxima Centauri as Earth receives from the Sun. It's the closest, potentially Earth-like world ever discovered. Most known exoplanets are hundreds of light-years away. Interesting to study with telescopes, but utterly unreachable by any spacecraft we could build. Proxima b is different. It's close in cosmic terms. It's right next door. We have a possible second Earth almost within reach. The question is, can we actually get there? At New Horizons speed, 36,000 miles per hour, the fastest we've ever achieved leaving Earth, Proxima Centauri would take approximately 78,000 years. That number deserves a moment to sink in. Human civilization, the whole thing, from the invention of agriculture to today, is roughly 10,000 years old. Everything we call history, the pyramids, ancient Greece, the Roman Empire, the Middle Ages, the Renaissance, colonialism, the Industrial Revolution, World Wars, the Space Age, all of it fits within that span. To reach the nearest star at our current best speed, we need to maintain a functioning mission for nearly 8 times longer than human civilization has existed. That's not a travel time, that's a geological era. Entire species evolve and go extinct on that timescale. To reach Proxima Centauri within a human lifetime, say 40 or 50 years, a spacecraft would need to travel at roughly 10% of light speed. That's about 67 million miles per hour. For context, that's nearly 2,000 times faster than New Horizons. Not twice as fast, not 10 times, 2,000 times. Several propulsion concepts have been proposed to achieve such speeds. None of them are easy. Nuclear pulse propulsion, detonating atomic bombs behind a spacecraft and riding the shockwaves, could theoretically reach 3 to 5% of light speed. Travel time about 100 to 150 years. Much better than 78,000, but still multi-generational. Fusion engines, like the theoretical Project Daedalus, designed studied in the 1970s, could potentially hit 10% of light speed. Travel time 40 to 50 years, almost achievable within a human career. But the spacecraft would weigh 50,000 tons at launch and require enormous quantities of helium-3, fuel we don't yet know how to produce. Antimatter propulsion offers the highest theoretical speeds, up to 40% of light, with travel times around 10 years. The problem? Producing a single gram of antimatter with current particle accelerators would take approximately 1 billion years of continuous operation. The most promising near-term proposal doesn't try to send a large spacecraft at all. It sends thousands of tiny ones. Breakthrough Starshot, funded with over $100 million, proposes a radically different architecture. Instead of massive ships, it would launch gram-scale probes, each weighing about as much as a paperclip, equipped with miniature cameras, sensors, and communication equipment. These tiny craft would be accelerated not by onboard engines, but by powerful ground-based lasers. The light pressure from concentrated laser beams would push them to extraordinary speeds. The target, 20% of light speed, roughly 134 million miles per hour. At that velocity, Proxima Centauri is just 20 to 25 years away. Add 4 years for the data to travel back to Earth at light speed, and we could have actual images from another star system within 30 years of launch. People alive today could see those images. The probes would be so small and moving so fast that many would be destroyed by interstellar dust during the journey. A grain of dust hitting a spacecraft at 20% light speed releases energy like a small bomb. But with thousands of probes launched, enough would survive. It's exploration through redundancy, accepting losses in exchange for certainty that some will arrive. This isn't theoretical physics. Real engineers are working on real components. The technology is extremely challenging, but it doesn't require new laws of physics. It's engineering, not magic. When you line up the numbers, a pattern emerges. Pluto, 9 years for a flyby, 27 years for an orbit mission, still within our solar system. Proxima Centauri, 78,000 years with current technology, maybe 30 years with laser-pushed probes that don't exist yet but could within our lifetimes. The distances are humbling. They remind us that space isn't a place we can casually visit. It's an environment fundamentally hostile to quick travel. The emptiness between destinations isn't just empty, it's vast beyond everyday comprehension. But there's another way to read these numbers. A century ago, reaching the moon seemed like pure fantasy, the stuff of fiction writers and dreamers. 50 years ago, we walked on it. Today, we're seriously designing probes that could reach another star within a human lifetime. Each generation pushes a little farther than the last. The edge of possibility keeps moving outward. We probably won't see humans walking on a planet around Proxima Centauri, but we might, just might, see the first images from that system arrive on Earth. A tiny camera launched by lasers traveling for decades through the void, sending back pictures of an alien world orbiting an alien sun. It would be a photograph from another star, proof that we reached beyond our solar system, a message sent across the cosmic ocean, and an answer received. The distances are vast, but we're learning to cross them, slowly, patiently, one generation at a time. We've talked about how far Pluto and Proxima Centauri are, But there's another question most people never think to ask. What's above the solar system? What's below it? The answer involves structures that surround us in every direction and connect us to the larger galaxy. Watch what exists above and below the solar system to find out.